Yep, there we go. So you can recognize it right away, and it starts recording. Okay, excellent. Right.
Finally got Linux running.
Yep, I finally got Linux running, which is kind of interesting because what got it working again was I basically stopped using the NVIDIA driver. So instead of using the proprietary NVIDIA driver for the NVIDIA video card, I used the generic driver, which is not published by NVIDIA, and that actually works better, at least with this particular configuration. That's just kind of interesting. All right. So what we'll do today is we'll take a look at the binary search algorithm, because last time we talked about how it is very efficient. Okay, to search for a single entry within about 8 billion. All I need is 33 comparisons to confirm that something is or is not in the array. Okay, I would call that pretty efficient. I mean, just think about it. 33 comparisons for 8 billion entries.
Just me or that screen's crooked?
I think the edge may be off a little bit, so you're seeing, yeah, I think the edge is a little bit off. I can use auto setup and see if it can. Yep, now it fixes itself. The screen may be crooked, like not flat.
That one. It's a little bit twisted.
Well, I cannot fix that one. Yep, so you have to tilt your head a little bit to fix that. So getting back to binary search, it is one of the most efficient. It is the most efficient search algorithm. In fact, you can prove that there cannot exist any faster search algorithms, given an array that is already sorted. Okay, those are the things that we will talk about that I will not talk about in this class. But when you go to a 4-year university in their computer science program, there is a class called algorithm analysis, or the analysis of algorithms, depending on the school, and that class will talk about all the math stuff, okay, of what we just talked about on last Thursday. But in this class, we just kind of have to appreciate the efficiency of this particular algorithm and why it is important. So just to recap what we talked about last time, it has to do with the complexity of the algorithm, or the time complexity of the algorithm. The time complexity of the algorithm is basically determining the shape of the curve of how the execution time relates to the size of the problem. I'll just use the whiteboard for this particular purpose. So we have a graph. On the horizontal axis, we have the size of the problem. So in this case, I use bar A bar as the horizontal axis because it is the size of the array, number of items in the array. In the vertical axis, we basically have time, and this doesn't have to be actual real time. It just has to be, time of some scale. In the first case, when Pat used a linear search algorithm, you can see that that curve is flat. In other words, it's a straight line. Whenever you make the problem size bigger, the amount of time that it takes is proportionally longer. Okay, you double the problem size, it will take twice as long to finish the algorithm. On the other hand, the binary search algorithm has a logarithmic curve. In other words, if you double the size of the problem, it will only add 1 to the time. Okay, you double the problem again, it will add another unit of time, on top of that. So that basically says, it doesn't matter how you scale everything. In other words, I can start with one of the slowest computers in the world, and Pat can start with one of the fastest computer in the world. It just changes how quickly I can catch up with Pat's computer. Okay, because the shape of the curve is different in this case. So when you look up algorithms in the future, okay, it can be your next class, can be cisp300, can be a few other classes down the line, can be when you are at work, with Google, Facebook, and all those really well-paying jobs, okay. Then the first thing you want to do is you can realize, most of you already know that Wikipedia has a lot of information, including algorithms. The scaling of everything is just off today. I cannot exactly put my finger on why everything just looks off, because if you look at the text on the URL, that looks a lot smaller than it should be. So I think the scaling is off somewhere. Okay, but let's go focus back on here. So if you look at binary search, okay, you can look at binary search in Wikipedia. I would not trust Wikipedia for anything else, but as far as technical stuff is concerned, especially algorithms, computer concepts, and stuff like that, Wikipedia is actually not a bad resource for all of those things. If you look at binary search, it's a fairly long page. I mean, you can see that the thumb bar, the thumbnail is actually pretty small, so when you scroll, it's pretty long. But what we need to focus on is worst case performance. In this case, it is big O of log of n. And n in this case represents bar A bar, which is the size of the problem. So this tells you that the amount of time it takes to complete the algorithm is proportional to the log of the size of the problem. Okay. Next, we'll go look up linear search just for comparison. So we look up linear search, using Google, and the first entry is the Wikipedia entry. And then we can look up the time complexity, which usually is listed here. I'm just going to look for, nope, doesn't have complexity here. Big O of n, there we go. Okay, so let me get rid of the search thing here. It doesn't have a specific entry for that, but you can kind of tell that the worst case cost and expected cost of linear search are both big O of n, which means the execution time is proportional to n, which is the size of the problem. So when you look at the big O notation, it doesn't tell you the absolute amount of time because that depends on what computer you're using. However, it does give you the shape of the curve, so to speak. So when you have big O of n, it means it's linear, like this straight line here. When you have big O of log of n, you're looking at some kind of a log curve, and the scale doesn't really matter because the scale is only determined by the actual hardware that you're using. Go ahead.
What exactly is big O again?
It's a notation in algorithm analysis to basically indicate what we call the time complexity of an algorithm. So it's just a notation. Are there any questions about this notation? I will not ask you any questions about the big O notation for this class, but it is something that is good to know because if you choose an algorithm that has a nice, optimal, big O time complexity, then you know for sure that you are picking the right algorithm because it cannot go any faster. On the other hand, if you just pick a algorithm, out of a whole bunch of alternatives, you may not be getting the best, the best time complexity, which also means that when you're testing it with a small array, it may work just fine. But if it doesn't scale well, with the size of the problem, then you can run into problems later because when you actually deploy the program in the real world, people will be throwing real test cases at your program, and you may not expect how badly the program may behave when you have a much larger test case. Okay, so this is just an exposure thing, not really the focus of this class, but it is something that you need to consider when you choose an algorithm to do something. I'll give you just two more examples, because you will run into this sort of thing in cisp300. So let's talk about sorting algorithms. They're fairly complex. I'm not going to talk about the details of sorting, at least not at this point. One really common one that most professors will talk about when they talk about sorting is called bubble sort. Okay, the actual algorithm is one of the easiest. Okay, if you want to look at the implementation of the algorithm, the logic is actually pretty easy. However, if you look at the worst case performance, it is big O of n squared, which means the amount of time it takes to perform bubble sort is proportional to the square of the size of the problem. If you double the size of the problem, it will take 4 times as long to finish the algorithm. If you triple the size of the problem, it would take 9 times as long to finish the algorithm. That's basically what the square is about. So it's not really particularly efficient. When you look at other types of sorting algorithm, such as merge sort, okay, and merge sort has a different time complexity. The worst case performance is this. In this case, it is big O. Okay, let me just magnify this a little bit. It's big O of n log n. So we are now comparing, big O n squared with big O n times log n. Which one do you think is better? Okay, so we are comparing the two curves. Okay, one is n squared, one is n times log of n. What base we are using for log does not matter because it just changed the scale of the whole thing. So which one do you think is a curve that grows faster, which makes it the worst algorithm?
N squared.
N squared. Okay, n squared is a worse algorithm because it grows faster. Is that making any sense? Okay. So if you have to choose between these two algorithms, not even understanding how the algorithm itself works, just by the published worst case performance time complexity, you already know which one is a better choice. Okay? And I think that is important because you have to kind of be aware of the whole issue of time complexity. Merge sort is complex. When you look at the algorithm itself, it is actually quite a bit more complex. Let me just zoom out again because I can't really fit everything into one screen unless I zoom out. Okay, that's basically how complex it is. It's basically two part. This is the first part. Okay, this is one implementation of merge sort. We are not going to take a close look at the details because it really is kind of complex. Okay, but this is merge sort. Bubble sort, on the other hand, looks a lot simpler. If you look at just the algorithm itself, bubble sort is just that. Okay, but do not let the length of the program fool you because the length of the algorithm in this case has almost nothing to do with the actual amount of time it takes to finish the algorithm. It's just like between linear search and binary search, which we will take a look today. Binary search is a longer algorithm in terms of the number of lines that you have to write. But in terms of execution time, it is far less than linear search, which is actually simpler when you just look at the number of lines. Okay. Are there any questions about this discussion at this point? No questions? Does everybody understand the importance of paying attention to the efficiency of an algorithm and how to assess the efficiency of an algorithm using just a Wikipedia entry? All right. So with that out of the way, what we'll do is we will try to write the algorithm, the bubble sort algorithm today. But before we do that, we'll go ahead and try to perform binary search by hand just a few times, just so that we get a hang of it, doing it manually. Once we know how to reliably do it manually, then we can go ahead and actually implement the algorithm in pseudocode. In this class, I am not concerned about how to translate a program already written in pseudocode into a particular programming language. Because translating something into a programming language, a particular actual programming language, to me, I think it is a fairly mechanical process. Now you might say, well, but I have no programming experience, so to me it's not really that mechanical. But over time, it will become mechanical. It's just like, how do you write a good story? Okay, how do you write a good technical paper so that somebody else can understand, a topic in science, a topic in engineering, and stuff like that? Okay, does it depend more on the language itself, or does it more depend more on your organization and what content you're putting into the paper?
They're both important.
They're both important, but once you have the content, let's say you have a technical paper written in English, okay, and it has really good content, everything is explained well. Do you think it's relatively easy to translate that into other languages, but preserving the content or the quality of the content? You need a good translator to do it, okay? But does the translator need to have the same depth of knowledge as you do? Probably not as much, okay? Technical terms, yes, okay, you have to translate technical terms from English to another language, which is not, necessarily easy. But at the same time, the person who's doing the translation does not need the same depth of knowledge of the subject matter. Is that making any sense? It's the same way with programming. If you have a good way of analyzing a problem and coming up with an algorithm, and you have the pseudocode, translating that pseudocode into PHP, Perl, C++, which is the next class that most of you will be taking, It's a fairly mechanical process. It's almost a one-to-one thing. Okay, if I see this in pseudocode, it looks like this in C. If I see this in pseudocode, it looks like this in C. So I would call that somewhat mechanical because it's just mapping something from one pattern to another pattern. But to come up with the algorithm to begin with is the difficult part of writing a program. All right, so let's go ahead and just write a use an example to illustrate binary search. Okay, so binary search only works on sorted arrays. So we'll go ahead and create an array that is sorted, and you can have duplicate items. Binary search, just like linear search, is only there to confirm whether a item of that value exists or not in the array. It does not have to be the unique item with that value. So it can be non-unique. Okay. So we'll go ahead and just initialize an array here, and I will just pick 7 items. Okay, 7 items is nice because there are only 6 here. Now there's 7. 7 is nice because it is 2 to the power of something minus 1, which means, well, everything would divide kind of nicely. Okay, you never have to kind of think about which one is the middle element. There's only one middle element in this case. Okay, so we'll go through a few iterations. Let's go ahead and try to find a particular value in this case, and I'm going to use a notation to basically denote the comparisons and also the result of the comparison, and so on and so forth. Which number do you guys want to find here? You guys can pick the number.
23.
23? Okay, so let's look for 23. 23 is the item, the last item in the array, and we can quickly locate 23 because we can kind of scan through all 7 items at the same time. But that is not a systematic approach because you cannot just say, I can scan through all the items and then find the one that we're looking for. What if you have 8 billion items? Can you scan through 8 billion items even though it's sorted? Probably not. Okay, so you need a much more systematic way and try to describe it. And binary search always starts with the middle one. Okay, so in this particular example, we are looking for 23. So what we'll do is we look for the one right in the middle of the entire array, which is the one on row 4 in this spreadsheet. It has a value of 10. So you compare the value of that item to the value that you're searching for, which is 23. And what is the result of 10 compared to 23? 10 is less than 23, right? Okay. So we'll just denote it as 10 is less than 23. Now, because the array is sorted and the algorithm understands the array is already sorted, if 23 is already larger than the item at index 4 in this case, or on row 4, what about the items above or below it? Can I say something about the items below or above it?
We know it's not items of any of the items above, so
Right.
lines 1 through 3, we know we can exclude those.
Exactly. So once you identify that 23 is greater than 10, you can basically say, it would apply to all of these items too. Okay, sorry about that. The spreadsheet is being a little bit too smart. Okay, so let me see if I can do this. Select both first. Nope, it's way too smart. Fine, I'll just have to type it. There we go. Does it make sense? One single comparison will help me deduce that well, even though I have only performed one comparison, but I can conclude that the first half of the array cannot contain the item that I'm searching for. Okay. Well, but I cannot say anything about the second half of the array. In other words, I would look at the second half of the array, which in this case have the values of 14, 20, and 23, and say, okay, this is the remaining portion of the array that might still contain the value that I'm searching for, and then what do I do with this portion of the array?
Start in the middle.
Start in the middle and compare the 23 to that item. Which item is the middle one now?
20.
20, yep, okay. So we'll compare 20 to 23, and of course, 20 is less than 23. So what I can do is to say that, okay, that gives me, about the same conclusion that, all the items at row 6 and before are less than 23. Now I have one item left. What is the middle item of the range that is left here? It is itself, right? Okay, but I cannot make a conclusion just yet that 23 is this item or it's not this item. I need one last comparison to make that conclusion. So in this case, I make another comparison here, and with this comparison, the conclusion is it is 23. And the funny thing is I cannot type just equal 23 because with most spreadsheets, when you type equal to, it kind of equates it to. I have to put a space in front of it because otherwise it will just do the equation thing and just try to calculate the value 23. So at this point, I can make a conclusion and say, okay, I just found what I was searching for, and it took me only 3 comparisons. Are we doing okay so far with the first test case? Okay, we don't have any pseudocode to actually follow. In this case, I'm just doing it by hand and just using the approach. We're trying to come up with the logic, the procedural logic to do this with pseudocode. All right, so that's our first one, and let's go ahead and test it a few more times. And you guys can tell me what you want to search for. If you think of one that is really tricky, go ahead and let me know, because the approach works for all values. 14. 14. Okay, 14. Now 14 seems to be a tricky one.
10.
Sorry?
10. What about 10?
What about 10? 10 is not going to be very fun because the middle element is what we compare to first. So the first comparison will make the conclusion and say, we found it. So it's not going to be very interesting. 19? Okay, let's try 19 and then we'll go back to 14 because 19 is a little bit more interesting because it is not there. Okay, so the question is, how many comparisons does it take for me to know that 19 is not there?
3.
Okay, it takes exactly 3 comparisons, but what are the orders of the comparison, and when can I make a conclusion that 19 is not there? Well, the first one is to compare to the middle one, so 19 is definitely greater than 10, which also implies that 19 is greater than all of the cells before the one that I just compared to. And this really is the essence of binary search, is you make one comparison, but it can draw conclusion about a big portion of the array and say, okay, we can rule all of these out as well. We only have 3 elements left. With the 3 elements left, which are these 3 elements, we will pick the one in the middle and compare to it. The one in the middle is 20. So you compare 20 to 19, and the conclusion is 20 is greater than 19. Okay, well that by itself is not really a big thing. But what is big about it is if 20 is larger than 19, then all the items below 20, because this is a sorted array, they also have to be greater than 19. So I can now rule out not just one element, but 2 elements of the entire array of potentially having the value of 19. I only have one row that has not been ruled out yet, which is 14. So at this point, I compare this row, which has a value of 14 to 19, and for 14 is less than 19, and because it is a sorted array, I can now also make the conclusion that all of the elements before that are also less than 19. If you combine these 3 columns, okay, if you combine column B, column C, column B, column C, and column D, don't you think that I have made a conclusion that none of the items in the array can have a value of 19? Because they're either less than or greater than 19, and there's nothing left that can potentially have the value of 19. So at this point, I can make that conclusion that 19 cannot possibly be in the array. It only took me 3 comparisons. I think 14 was one of the cases that people want to look at. So we'll take a look at that one too. And we'll use exactly the same array to begin with. And then see what we do with the case of 14. So the first comparison is against 10 again. 19 is greater than 10. And as a result, we conclude that these 4 items cannot
14.
be.
14.
Oh, 14, that's right. Sorry. 14. Keyboard shortcut. not warn me. Future? All right, there we go. Okay, now we have ruled out the first 4 items in the array. Let's look at the three remaining items. So we have 3 items remaining, and these can potentially be 14 at this point because I don't know for sure. So we pick the one in the middle and compare that. 20 is greater than 14, which also means the 23, or all the items below 20, would also be greater than 14. So now at this point we have only 1 row left that is unmarked, which means it can still potentially be 14, but we have to have one last comparison to confirm that this is actually 14. And once we match that item, then we can make the conclusion and say that, okay, we just found what we were searching for, and it is time to exit the loop. You're done. Are there any questions about the binary search process, how it works? No? Okay. Let me just add one more test case, and then we'll go ahead and try to write the pseudocode. Let's try to look for 1. Okay? 1 is not in the array. In fact, it is all the way at the beginning. Okay? Because let's take a look at how it works in this case. Some of you probably already have a general idea of how it's going to work out, but we'll go take a look anyway. This time we're looking for 1. We still pick the one in the middle to compare to. 10 is greater than 1. Now, if 10 is greater than 1, then all the items below 10 will also be greater than 1. I don't need any additional comparisons to make this conclusion because the array is already sorted. Okay? So with one comparison, I'm ruling out 4 possibilities. I have 3 possibilities left in this case. Of the 3 remaining, I pick the one in the middle for the comparison. So that will be this row here with a value of 5. 5 is also greater than 1. Now, if 5 is greater than 1, then all of the items below that would also be greater than 1, like that. So at this point, I have 1 item left, which is the one on row 1, that can still have a value of greater than 1, equal to 1. But once I make that comparison, it is clear to me that none of the items can be equal to 1, because now I know that all of the items in the array are greater than 1. And at this point, I can exit the algorithm because I have no items left to track that can potentially have the value that we are looking for. Is that okay so far? Okay. All right. So the next thing we want to do is to look at all these test cases that we have done by hand and try to come up with the algorithm that can do exactly that, but we can tell a computer to do it this time instead of us doing it by hand. Okay. All right. So let's go to this notepad here. We call it mouse pad, but the same thing. And I have to readjust the font size because it just did not preserve the font size that I have used in the past. Okay, that's pretty big. All right, so just like before, let me turn off the line number because we really don't need a line number in this case. Okay, so the first thing we want to do whenever we come up with an algorithm is it repetitive? Are we doing something over and over again? Yep. Okay, so we'll just go ahead and make a note of, yes, we are doing something over and over again. So we'll just call this revision 1 so that we can refer back to it. So we have some kind of a loop. And remember, when I say loop and loop, I simply means that there's some kind of a loop here. I have no idea whether I should use a pre-checking loop, the while type, or a post-checking loop, the repeat type at this point. I just know that something is being done over and over again. With very few exceptions, most loops need to exit. In other words, you have to kind of tell the algorithm, are we going to exit? And if we are going to exit, when are we going to exit? Okay? So we want to specify when we are going to exit in this case. This is a search algorithm. With any type of search algorithm, if you just look at the top level logic, we exit when one of 2 conditions is true. Okay? One is when we confirm that we have found the value in the array. Okay, there's no argument why we should exit the loop at this point because we just found it. Okay, we have a conclusion. And then the second reason to exit from the loop is when we have concluded that no item in the array can potentially have that value. Not just the one that we are comparing at this point, but also we know that none of the items in the array can potentially have that value. Okay? So we want to capture that logic here and just kind of write it out, as a phrase instead of actual pseudocode. Okay? So we'll just say, when we found the value in the array, or we confirm none of the elements has the value that we are searching for, or otherwise known as the key. Okay, is that okay? Does everybody understand, what I have captured at this point regarding the logic of this search algorithm? Does that look like what we had before with linear search? A little bit. I mean, linear search, has all the same elements of, when to get out of the loop. Okay. So just about any search algorithm will have, this reason to get out of the loop. Are we doing okay so far? Okay. Revision 2 is going to say, well, let's use some variables. Okay. What array are we talking about? What value are we talking about? Okay. So in revision 2, I'm just trying to, clean it up a little bit by introducing, an array as a variable and also a key which represents the value that we are searching for. So these are the two variables that we're going to introduce just so that we can more clearly refer to the items in the array. Okay, so we'll just say, let A be the array containing some elements, and then let K be the value that we are searching for. Okay. Now with these two variables defined, I can now go back and look at this algorithm here and say, well, can we use these two terms, when we, look at, each phrase? We found the value in the array. Now, when we say that we found the value in the array, it means, some element in the entire array has the same value as K, right? I mean, that's basically what it means when we use the phrase that we have found the value in the array. Okay? So we'll just go ahead and use a very obscure and ambiguous thing to represent that. Okay? Because A itself is an entire array. I cannot compare an entire array, which is a box of coffee mugs, with a particular value. It doesn't make sense. Okay? But I can say, hey, one of the items in the array is going to match the value of K. That makes sense. But I don't know how to specify that item yet. Okay, so I just put a question mark here and say, to be specified. Okay. So if you do not like the notation of a question mark, you can use, TBD, for to be determined. Okay, I just don't know how to specify it yet, but I know that, the rest of the notation makes sense. The second one, it's a little bit harder to express, because how do we express that none of the elements has the value? Now, if you have taken a few classes in mathematics, you might understand the notation of there exists for all, that sort of thing, which makes it possible to express it here. But I'm just going to keep it the way it is for the time being, okay? Because I think we can solve this problem maybe a little bit later. And that's my revision 2. And you can see that revision 1 and revision 2 are not really that different. It's just that we introduce a particular term called array A, or two terms. One is array A and one is the value K, or the variable K which stores the value that we are searching for. Okay, in revision 3, then we start to think about, all right, so how does the search mechanism work in this case? So now we are actually going deeper into the details of the binary search algorithm. In other words, we look back into the spreadsheet with each test case that we have, starting with sheet 1 here. Okay, we start with the entire array, and then after one comparison, we know that the first 4 items cannot have the value of 23. After the second comparison, we know the first 6 items cannot have the value of 23, and then after the third comparison, we found the item because that's the only thing left to compare. In sheet 2, it's a little bit more tricky because in this case, after the first comparison, we know the first items cannot have the value of 19. After the second comparison, we know the last 2 items also cannot have the value of 19. Okay, but this one is kind of weird in a way because I am ruling out items both before and after. Okay? Before the third comparison, I have only one element left that can have the value of 19 potentially, because at that time I do not know the value of that particular item on row 5. But it's in the middle. Okay? In other words, in this case, I'm ruling things out before, I'm ruling things out from the bottom, and the range that can still contain the value is actually somewhere in the middle. I need a way to keep track of that range of indexes that is representing values or elements in the array that can still match the value that I'm searching for. Okay, so I'll just go ahead and write it down, in my notepad here, and I'll just spell it out. Okay, I need a way to keep track of which part of the array may still contain elements of value k. Okay? Is that making sense so far? Because I know, that we are trying to keep track of that part of the array, and every single time we look at that part of the array and say, okay, pick the one in the middle and you perform another comparison.
How would you know that if the item exists in a list that's over like 800,000 or something like that?
How do I know the item exists?
Yeah, in a large.
We basically use the same method. The method applies to no matter how large the array is. Whether you have 7 items or 7 gazillion items or 7 billion items does not make any difference.
Or you need 3.
Hmm?
You need to just look at it.
I look at which portion of the array can still have the value that matches k, and then I just say, okay, who is right in the middle of this range? Make the comparison, and then rule out either the first half, the second half, or say, oh, okay, this is my lucky day. This is exactly what I'm looking for. Because each time, you can only have one of those 3 conclusions. Okay. All right. So now that I am, thinking about a way to keep track of which part of the array may still contain the elements of value k, don't you think this concept here, which part of the array may still contain elements of value k, has something to do with we confirm none of the elements has the value that we are searching for? Because initially, the entire array may contain the value that we're searching for before the first comparison. Do you guys agree that before the first comparison, we cannot rule out anything? Okay. But after each comparison, we kind of, chop the array down into like half the size, or the range of elements that may still contain the value that we're searching for. We're reducing that number by 50% with each comparison. Okay. So the question now is, how do we link this statement? I need to find a way to keep track of which part of the array may still contain elements of value k, okay, as opposed to we confirm none of the elements can have the value k. What about this? What happens when this part of the array has no elements? In other words, what if, quote unquote, the part of the array that may still contain elements of value k is none? Isn't that the same thing as concluding that none of the elements has the value k? Okay, so we'll go ahead and change the way we phrase this now. So instead of saying this, we're going to use this terminology, which basically says the part of the array that, okay, since we have the notion of A at this point, we are just A, the part of A that may still contain elements of value k is empty. Is that okay? Because what I'm trying to do is to kind of use the same notation, so that if I have the concept of keeping track of which part of the array may still contain elements of value k, I'm going to use that terminology in the condition and basically say, if that part of the array becomes empty, we just make the conclusion that whatever we're looking for, value k, is not in the array. Would that be okay? Yes? Kind of? Okay. And I call this my revision 3, so I'm gonna move on to revision 4 at this point. Now the process of going from one revision to the next, there's really no way to describe what goes through my mind to go from one revision to the next. It's really just going step by step and go, okay, what can I do at this point? And for whatever reason, my mind just tells me, okay, this is what you need to do as the next step. So this is me trying to explain that process the best I can, to kind of deal with the writing of an algorithm in a very step-by-step fashion. All right, revision 4 is basically going to look at, but how do I represent which part of the array may still contain elements of value k? So to illustrate this, we can go back to the spreadsheet and say, all right, so what we can do is we can highlight, okay? We can use a highlight here and basically say, okay, we'll use a highlighter to denote which part of the array may still contain the value k. Originally, before the first comparison, this entire range can contain the value that we are searching for, because this is done before the first comparison. I cannot possibly rule out anything at this point. Okay, so we'll go ahead and color the entire range and say, well, anything in this array may contain the value 23 at this point, because this is before I make the first comparison. After the second comparison, which is denoted by column B, the first 4 rows are now ruled out because we compare to the 4th row, and because the array is sorted, once we know 23 is greater than 10, all of the elements before we can rule out also. So at this point, we have 3 elements left that may contain the value 23 that we are searching for. After the second comparison, we compare 20 to 23. We make the conclusion that 20 is still less than 23, which also means everything before 20 would also be less than 23. So that means whatever is after, there's only one element left that can contain the value k. So we highlight this part here as the only thing left after the second comparison that may still have a value of 23. And obviously, in the third comparison, we make the conclusion and say that, aha, okay, it is the one that we're looking for. And at that point, even though we don't need to denote which part of the array may still have the value anymore, because we just found it. Is that okay so far? Does everybody understand what the yellow highlight is representing in the spreadsheet? In each column, the portion that is highlighted yellow is representing which part of the array may still contain the value that we are searching for. Okay, is that okay? So you can see that it's almost halving each time. We went from 7 to 3, 3 to 1. If you have a really large number to begin with, like 2 to the power of 10 to begin with, minus 1, the next one would have 2 to the power of 9 minus 1, and then the next one would have 2 to the power of 8 minus 1, and so on. Okay. All right, let's look at the second spreadsheet and see if we can use this highlighting mechanism here. This one is tricky, okay? So we'll take a look at why it is tricky. Before the first comparison, we can say, oh, anything in this entire array may be 19. Fine. We'll just use the highlight to denote that anything here can have the value of 19. In the second column, we pick the one right in the middle of everything, of the range of the array that may still contain the value 19, and we make a comparison right in the middle. And we make a conclusion that 10 is less than 19. But because the array is sorted, we can also rule out the first 4 items at this point of not having the value of 19. Saying that the first 4 items cannot have the value of 19 is basically saying these 3 items may still contain the value 19. So I'm going to use the highlight here and say that, well, we have 3 items left that may still have the value 19. And here's the tricky part. The really tricky part is in the second comparison, we compare to 20, and 19 is less than 20. But because the array is sorted, we can make the conclusion that this item and everything below that cannot match the value 19 also. So that means we have ruled out these 4 items from before, And now we are ruling out these two items. What is left? Which row is left to potentially have the value of 19? Row 5, exactly. So this is the only row that we should highlight. Okay? And after the third comparison, represented by column D, now there's nothing can be highlighted with the yellow highlighter because we have just ruled out every single cell. Right? Because the only thing that is left, which is row 5, that we thought in column C that may still contain the value of 19, is now ruled out. Okay? We know that 14 is less than 19, and it cannot have the value of 19. Okay? Is that making any sense? Okay, going from one column to the next. And we'll just take a look at another test case here. This one is the same way. Okay, before the first comparison, anything in the array may contain the value 19. After the first comparison, I only have 3 items left that may contain the value 19. After the second comparison, I have only 1 item left. And after the third comparison, I just found that, hey, the only item left that may contain the value 14 is the one that has the value of 14. And that way I can get out of the loop. All right? All right. So what we need to do is to go back to the algorithm. We'll go kind of back and forth a little bit here. We go back to the algorithm by saying, I need a way to keep track of which part of the array may still contain elements of value k. And then we go back to the example here. Hey, isn't that really just the portion that is highlighted yellow within each column? There was a question. Oh, row sheet. Thank you. So in this case, we are just keeping track of, which part of the array is still highlighted yellow. So I'll let you guys kind of think a little bit about, what would be a good way to represent the yellow portion that may still contain the value k. Okay, how do we keep track of that shrinking yellow portion?
Red.
Hmm?
Red color.
Sorry?
Red.
Breadcrumb?
No, red. Finger. Make it red color.
Red color? Well, we already have the yellow color to do the same thing, right? So the question now really translates to, in an algorithm, how do we keep track of that? Okay. And I'm going to pass the worksheet here. All right. One thing that we notice is the yellow portion is always contiguous. In other words, we never have a case where we have yellow portions spread all over the place, or yellow regions spread all over the place.
Start the end value for the yellow portion.
Yep. You can keep track of the beginning and the end of the yellow portion. Is that making any sense? So imagine this is a phone book, okay? And this time, it's a regular phone book, and we're searching by name, okay? So the approach that you might want to use in this case is to start with 2 bookmarks or 2 little post-its, okay? Each post-it, one post-it, will mark the beginning or the first page that may still contain the name that you're searching for, and then another bookmark or another post-it will mark the last page of the entire phone book that may still contain the value or the name that you're searching for. Is that okay? So you have 2 little post-its. Initially, you put the first post-it at the very beginning of the entire phone book, and the second post-it all the way to the end of the phone book. Because before the first comparison, the entire phone book may contain the name that you're searching for. Is that making sense? Okay, so now, yep, go ahead.
Okay, so are we talking about building an index within an array that has separate values, like A through F or G through L, or?
No, it's a regular phone book, so it's just alphabetically sorted. Okay, I can kind of pictorially represent it. Okay, so let's imagine that you're looking at a phone book, and so we have a really, really thick phone book here. Okay, this is the entire phone book, all right, and has like hundreds and hundreds of pages. And you look at this phone book and go like, okay, I need to find a particular name, but instead of using the usual approach of okay, flip open it and then kind of guesstimate where to go, I will try to apply the binary search algorithm here. So what you do is you have 2 bookmarks or 2 post-its that you can move around. initially I put one bookmark all the way at the beginning, and one bookmark all the way at the end of the entire phone book. Because it is marking that the name that I'm searching for is between this bookmark and this bookmark. Is that making any sense? That's how I keep track of which part of the phone book may still contain the name that I'm searching for. And where do you think I will be comparing, or which page do you think I would make the comparison? Yep, I just look at the thickness of the book, phone book, and guesstimate. I don't have to be exact, I just have to kind of guesstimate and find out, okay, which page is approximately at the middle of the entire range here. Okay, so let's say it is this particular page here. I make my comparison, and I confirm that the name that I'm searching for is not on that page. Okay, what would be one of the two things that can happen if the name that I'm searching for is not on the page that I flipped to, which is right in the middle of this entire range?
You either move the top postmark there or the bottom.
That's right. Okay, so what he said was I can either move the top tab or the top bookmark all the way to one page right below this page, or I can either do this, or I can move the bottom page or bottom bookmark all the way up to one page before the page that I just searched in. Is that making any sense?
I have a question.
Yeah, go ahead.
How exactly, let's say that there were an even amount of items in your array here. How
Mhm.
exactly is it gonna determine?
It can be one or the other.
It doesn't matter?
Doesn't
Just
matter.
this one?
That's right. And that's why it works in a phone book too, because I don't need the exact middle, I just need somewhere close to the middle. Yeah, because the approach would kind of self-correct. Okay, as long as you're close to the middle, you're still going to have the same efficiency that we're looking for. You might be adding one or two comparisons to the entire thing, but it wouldn't be a whole lot, even if you cannot go straight to the middle. So I can either move the top bookmark down to one page below what I just compared to, or I can move the bottom bookmark to one page before the page that I searched in. Okay, and let's just pick one example here. So let's say that this is what we did. Okay, we moved the bottom bookmark up to the middle part, and then what do I do? The two bookmarks are still serving the same purposes as before. The first one, marks the first page that can contain the name that I'm searching for. The second bookmark marks the end of the range of the phone book that can still contain the name that I'm searching for. Okay, so what do I do at this point?
So you search between the top two now.
The middle part between these two bookmarks, right? Which is right about here. I make this comparison, so let's say this time I have to move the top bookmark to this portion here. So after the second comparison, I would have one bookmark here and another bookmark approximately over here, right? And then I would just take a look at the thickness in between and pick. I think this one is close to the middle of this. Make another comparison. I move either the top one down or move the bottom one up. So you can see what is happening is the two bookmarks originally spaced really, really far apart. Each time I make a comparison, they get closer, and then closer, and then closer, closer. Sometimes I move the first one forward, sometimes I move the other one backwards, but it doesn't matter, because every time I move it, I'm eliminating one half of the remaining choices. Is that making any sense? All right. Well, that's great, because instead of using a bookmark, can't I also just use two page numbers for the same purposes? Okay, because I have one page number representing the beginning part of the phone book that may still contain the name I'm searching for, and use another page number to represent the last page that may contain the name that I'm searching for. Is that making any sense? So instead of using bookmarks, I can use a page number. And if I can use a page number in the analogy of using a phone book, is there any concept that we can use to help us keep track of the range of the array that may still contain the value that we are searching for?
Array indexes.
Array indexes or variables, right? We just need two numbers in this case, or two variables to keep track of the first index and the last index of the array that may still contain the value that we are searching for. Okay. All right. And this is really the tricky part of writing an algorithm is, how do we solve a problem But you can see that I'm trying to solve the problem really step by step. Because at this point, from revision 3 to revision 4, my focus is not even the algorithm itself. My focus is how do we represent which part of the array may still contain the element that we are searching for. Okay, I'm not looking at the overall algorithm at this point. I'm not saying how do we compare. I'm just saying how do I keep track of this portion. Okay. So in revision 4, I just solve the problem. So what we'll do is we'll introduce two variables in this case. So I have variable b, the index of the first element in array A that can be of value k, and we have a matching for the end. So let E be the index of the last element in array A that can be of value k. In other words, B and E are analogous to the two bookmarks, with the phone book analogy. One to keep track of, okay, where do we start? And the other one to keep track of where do we end. And each time we perform a comparison, we either move the beginning forward or we can move the ending backwards. Is that okay? Now we have a pretty good way to represent the range of the array. Let's go back and look at the algorithm here and see if we can improve the algorithm or the way we say things here. I think once we know about B and E, we can kind of talk about the part of array A that may still contain elements of value k, because this portion seems to have something to do with B and E. The only question now is, how do we know that there's nothing left?
When B equals E.
When B equals E, okay.
Or K. It would be K. K is the value you're looking for, right? So
K is the value that we are searching for,
so you're
which is the phone number.
You're looking to see if either B or E is either greater than or equal to or less than. And then you would determine what to do based off of that.
Okay. Now, if you look at the definition of B and E, okay, it tells you something that is quote unquote natural to B and E. Because B is the index of the first element in the entire array that can be of value k, which is analogous to the first bookmark posted in the phone book. And E is the index of the last element in array A that can be of value k, which is analogous to the second bookmark on the phone book. Okay? Don't you think the first bookmark is usually before the second bookmark? Because even though we are moving them closer and closer together, they should not cross over. Now, can they be on the same page? What happens when they're on the same page? In other words, what if B, which is the index of the first element that can be of value k, the index of the first element that can be of value k, is the same as E, which is the index of the last element in array A that can be of value k? What happens when they overlap exactly? What if they are the same value?
It's the only possible choice that could be where K could be contained.
You only have one element to compare to. But I cannot make a conclusion that it is not found yet, because I still have that one page in the phone book to search for the name that I'm actually looking for. Okay, is that making any sense? Because it's analogous to these two bookmarks landing on the same page. Okay, marking that, oh, okay, this is the one page left for me to search. Yep.
So it's like saying if B is equal to E but does not equal K, then we've confirmed it's not there.
K is out of the equation. We don't use K in this case because we are only trying to determine, is there still anything in the array that may still contain the value K? And that range is only determined by B and E. K is out of this equation altogether.
B is less than or equal to E.
B is usually less than or equal to E. Is that making any sense? In other words, if you look at this analogy with the phone book, this is actually our B, this is actually our E. B started all over here, at the beginning all the way over here, and E started off all the way down here at the beginning. And after each comparison, we move one or the other so that they become closer and closer together. Now, if you're unlucky and they have to be landing on the same page at some point, that means the beginning of the range and the ending of the range is landing on the same page, which basically means you have one item left to compare. So B equals to E is not a condition for you to conclude F is not there. What do you think is? Okay, B is usually less than E. It makes perfect sense, okay, because now you have multiple pages to search in. B equals to E is still okay because now you have one page to search in. What happens next? If the item is not found here on this page, what do you think happens?
It's greater than E.
Yep. When B is greater than E, then we have a problem. Because that means there's no item left. You cannot have the index of the first element in an array being greater than the index of the last element in the same range of the array. Is that okay?
How exactly
I
does that
don't-
work?
Yeah, I'm just trying to figure out in what scenario that would
Okay.
actually happen.
So we'll just kind of write down here first, of this observation, okay? So instead of changing this part here, and we'll just say here that B is less than or equal to E, usually, okay? We'll just say usually, and it's really ambiguous. But we have this observation that B is usually less than or equal to E. So, okay. So the next revision would say, okay, now that we have B and we have E, don't you think that we know what to compare to with each iteration? We have, this TBD is now determined. I have a way to determine, the index of the element that I should compare to. Is that making any sense? It's just like in the phone book analogy. If I have this posted here and I have this posted here, I can kind of use these two to help me determine which page I want to compare to.
B plus E divided by 2.
Yeah, B plus E divided by 2 is the index of the element that we want to compare to. Okay. All right, so let's go ahead and do this part here. And we'll call this revision 5. In revision 5, we'll just say, let M be the index of the element that we compare to in each iteration. Because I have a feeling that we have to do that, we have to make use of M multiple times. So that's why I'm going to use a variable to represent it. All right, so I'll just copy and paste the actual algorithm here. And we'll say, hey, no, we don't need to say TBD to be determined anymore because we now have named the index of the element that we want to compare to. We just name it M. Okay. The big question is, how do we calculate M? But you just said, M is right between B and E, so we can say M is B plus E divided by 2. Okay. Yep.
We still need to convert it to integer.
Yeah, we'll worry about that later, okay? Because we just want to capture the concept first, okay? We just want to capture the main concept, and then all the details we'll handle later. Okay, so we know, M is somewhere, right in the middle of B and E, okay? Sometimes it doesn't divide well, but you know what? That's detail. We'll deal with that later. All right. Well, that's revision 5. Revision 5 is actually very important because now we have a way to determine which one or what is the index of the element that we are actually comparing to. But once we have that, then we have some additional things to do. Because if you go back to the spreadsheet, you will see that after each comparison, we have to move one or the other one. Okay? In this case, this has, okay, in column A, this was B, and this was E. Okay, is that making any sense? But then after the second comparison, we move the beginning all the way down here. After the after the first comparison, we move the beginning down here. After the second comparison, we move the beginning all the way down here. Okay, and that's how we found out. Okay, we only got one element left to compare, and it is 23. In the second test case, before the first comparison, this is the beginning, this is the end. After the first comparison, we move the beginning all the way down here. This is still the end. After the second comparison, we move the end all the way back so that it coincides with the beginning. So this way we have B equal to E, which is indicating that we got one element left. And then obviously after the third comparison, we just say, oh, okay, I guess that's not E either, but now we have nothing left. Because at that point, the beginning is going to be all the way down here, right here, and then the ending will be all the way up here. So they basically cross over. Okay. Okay, so let's kind of keep this picture here. I'm just gonna put it on the side so we can still take a look at it while we work on the pseudocode on this side. And I'm gonna change the font just a little bit so that we can show both the algorithm and the picture at the same time. Okay. All right. All right, so we know there's a comparison happening, right? We have some kind of comparison, comparing A bracket M. Okay, so we'll just say compare A bracket M with K. Okay, well, that's good. Okay, we can make a comparison. But what are we going to do about the result of the comparison? What outcome can occur after a comparison between two numbers?
We'll either set B equal to M plus 1 or E equals
What
M
about the
plus
comparison itself? Let's start with the comparison itself. Okay, after a comparison, what can be the possible outcomes of a comparison of numbers?
Greater than, less than, or equal to.
Okay, so let's go ahead and say what to do with each case. Okay, if I'll just use pseudo code in this case. If equal to, based on the previous comparison. Okay, if equal to, then we say
Eureka.
yep. You just found it. Okay. Else if less than, we do something. Else if greater than, we do something. Okay. Now this is not the final logic, okay, but I am doing this, so that it is just easier to analyze because out of a single comparison, we can only have three possible outcomes. Okay, we can have equal to, less than, or greater than. Okay. So the less than case is basically saying A bracket M is less than K. When A bracket M is less than K, which one are we moving? Are we moving B or are we moving E?
E.
Okay? So if A bracket M is less than the value that we are searching for, we are moving B, not E. Okay? We're moving B in this case. So how are we moving B?
To A bracket M plus 1.
Not A bracket M, because A bracket M refers to the value of the element. We are more interested in the index of the element. In other words, we are more interested in the page number as opposed to the names of the page in the phone book. Go ahead.
Just M plus 1.
M plus 1. Okay, M plus 1 is correct. Now, we kind of know that it's related to M, right? Because, A bracket M was, the one that we just compared with K, and the conclusion in this case is A bracket M is less than K. So we know that we have to move the beginning to somewhere around M, but we cannot make it exactly M. It doesn't make sense because B is representing the index of the first element in the array that may contain value K. But we just found that that element is less than value K, right? So it cannot be equal to K. So that's why it cannot be M. But what about the next item? Hey, you know what? The next item may just have the value of K. So that's why we need to use M plus 1 to change B, and not just M. Is that okay? It's kind of like in the phone book case. Okay, so let's say this is, these are pages on the phone book. This is, I had, E here. So this is the first page, this is the first page that may contain the name that I'm looking for, and this is the last page that may contain the name that I'm searching for. So I just split to the middle part of this, this range of pages here and say, okay, this is the page that I'm gonna, search for the name, that I'm looking for. That's M. Okay, And let's say, all of these names on this page are after the name that I'm searching for. Okay? In other words, I'm searching for a last name that starts with M, and everything on this page start with the letter T. Okay? So what do I do? Which one do I move? I'm searching for something that starts with an M, and everything on this page start with a T. Sorry,
Move the E up.
we move the E up. Okay, so the question now is, should I move the E all the way up here, or should I move the E all the way up to one page before the one that I just looked into?
One before.
The one before, because why would I make it the one of the page that I just searched in? Because I already confirmed that it does not have the name that I'm searching for. So that's why you have to move it one step before, and for the same reason, when you're moving B forward, you have to move it forward by one page, because in this case, A bracket M, we just compared it. We just compared and know that A bracket M does not have the value that we're searching for, and that's why B cannot be just M, it has to be M plus 1. And for the same reason, we just did this a little bit earlier, using the phone book analogy. If A bracket M, which is an element in the array, is greater than the value that we're searching for, then we have to move the ending to M minus 1 and not just M, because we just compared A bracket M with K and confirmed that it is not the same. So why would I want to say that that is the last element in the array that may have the value K? We just confirmed that it does not. Is that making any sense? Because that plus 1 and minus 1 makes a huge difference. If you forget that plus 1 or minus 1, binary search can turn into an infinite loop. Okay? All right, so we have most of the logic down already, and we got at least 5 more minutes to go in this class. So we have enough time to do it now. Okay? Is this answering the original question of how do we, represent this part here? Or what is the normal relationship between B and E, and when it is quote unquote not normal, and say, okay, this is weird, and I think we should get out now. Okay, B starts off all the way at the beginning, and E starts off all the way at the end. With each step, I move one or the other so they become closer to each other. That part we know, right? At some point they're going to overlap, which means in the phone book, I have B and E being on exactly the same page, which means I have one page left in the phone book to look into. After that one single comparison, we will either go, okay, remember, to get into this condition here, B and E are the same when we have one page left to look into. If A bracket M does not equal to K, I will not be executing this branch. I'll be executing this branch or this branch here, because it's either less than or greater than. But that will move B one step forward or move E one step backward. And remember, B and E and M were exactly the same to begin with. If you move B forward or move E backwards, they will start to cross over. You can no longer maintain the relationship of B is less than or equal to E, because B will end up greater than E. Is that okay? And that's when we know there's nothing left in the array to search in. In other words, this entire portion can be represented by a simple comparison of B is greater than E. And this is, I know it's kind of tricky, but it does work out. In the next class on Thursday, we will go ahead and trace this, using a few examples, possibly the same ones that we went over today using the spreadsheet, so that we can see the algorithm in, at work. And we'll finish up this algorithm. We have enough time to do that in revision 7. So in revision 7, what we'll do is we'll clean up this logic here, okay? Because we obviously do not have pseudocode to represent it. So we can say if A bracket M is less than K, then we move B forward to M plus 1. Else if A bracket M is greater than K, then we move E forward, backwards to m minus 1. What about the equal one? What about the eureka one? If you look at the highlighted code here, what about eureka? Do I have to do anything if they are the same?
No.
No, there's nothing to do when they're the same, because the loop exit condition is going to catch it too. So when they are the same, there's really nothing to do. So I'm going to erase that part from this code here. And you know what? That looks almost like a real algorithm now. Okay? The only thing left is to decide what to do with this loop and loop thing, because we know that we have to translate it into either while do, which is a pre-checking loop, or a repeat until, which is a post-checking loop. The difference between those two is with a repeat until, we have to perform at least one iteration before we get to test the condition. With a pre-checking loop, we test the condition first. The condition that we need to test is this condition here, and the body of the loop is here. So the biggest question is, can we perform this comparison first? What would be the value of m if I turn this into a pre-checking loop?
What the array is? What the array is, like the entire array. So like in our iteration here, like 7, I guess,
Right.
because we have 7 items.
But m is not 7. M is the index of the element that we're comparing to, so it would be 3 in this case. With 7 elements, m would be 3 to begin with, because it's the 4th element in the array with an index of 3. Okay? And the calculation of m depends on the loop body itself. So that means we have to perform at least one iteration before we perform before we check the condition. So this has to be a repeat until loop. It cannot be a pre-checking loop. It has to be a post-checking loop, because the one thing that we need to perform the comparison, which is m, is determined by the body of the loop itself. So that's why it cannot be a pre-checking loop. Now we do have 2 more things to take care of, which is the initial value of b and the initial value of e. What do you think is the index of the very first element in the array that can have the value k before the first comparison?
0.
0, yep. And what about the last element, the index of the last element of the entire array?
A bar minus 1.
Bar a bar minus 1. Yep. That's it. That's the entire algorithm with one thing left and 1 minute left to say it. If I have a variable found to indicate whether that element was actually found, how can I tell after the loop? After we get out of the loop, what is an indicator that we did find the element? I don't care the index of the element, so m is not important to me, but I do need to know, did we find it? True statement.
Yeah, A index n equals K.
Okay, there are 2 ways to say it. This is one way. That's one way to do it. But how do I know m is okay at this point? I mean, how do I know that m is not out of range at this point?
B less than equal E.
Well, because in the very last iteration, b has to be in range, e has to be in range. So if b and e are both in range, the average of those 2 has to be in range as well. So that's why we know that m has to be in range. The other way to say this, instead of using a bracket n equals k, we can also use if b is less than or equal to e. That's the other thing to use to indicate that the value that we are searching for is actually found in the array. So there are 2 ways to say it. I'm just going to write it out here so that it is recorded. So found, can also be expressed as, just b is less than or equal to e. You can use either one. They both work. All right. So we are done for today. On Thursday, we'll come back to the same algorithm. But on Thursday, what we'll do is we'll trace it with the test cases that we did by hand today. So this way we can see, okay, we know how to do it by hand, but what about the algorithm? What is it going to do when we run it as an algorithm?
Someone was saying that something like this, so I don't understand.
you have to evaluate the expression inside the square bracket first.
Yeah, I know
And then
that.
and then you use it to go to a particular element in the array. Whatever the value of the array element is becomes the right hand side. Okay, what does the square bracket notation do?
That's the element, like the number of the array. I mean, the number. Like, let's